Hi, this is our Beam Bridge project by Tanner Hall, Connor Krieger, and Abigail Standard. We decided to name our team the Warren Buffetts, and we know Warren Buffett has nothing to do with Warren Bridges because that's what we did our project over. But we felt like we had to name our team that, especially with this picture, because he accurately depicts how confused we were by this project. Also, the bridge on the right is not a Warren Bridge, but Tanner found it aesthetically pleasing, so he decided to add it to our title slide. Project description and specifications. So the Beam Bridge design project's goals were to model and construct a bridge that meets the feasibility and merit-based criterion, and then compare the predicted bridge weight, failure load, performance ratio, and safe load to the constructed bridge's measurements. Okay, this is the feasibility criteria. And this was used for the Beam Bridge project. Here we go. The inside of the bridge must be 2 inches wide and at least 1 inch high. The inside of the bridge must be able to accommodate a road bed, so no sharp peaks. The bridge base must be between 9.9 inches and 13 inches wide. The bridge base only contacts top surface of buttresses. The eye bolt and chain for testing can pass through the center of the bridge. The testing block, which is 3.5 inches by 3 inches, can be supported on the top of the bridge. The bridge uses open style truss construction. The bridge can be constructed with 1.5 8-inch by 1.5 8-inch balsa wood beams and wood glue. And an object which is 3.4 inches wide and 1.82 inches tall can pass under the center of the bridge. So this is for that last feasibility criteria point. This is the diagram of height and length feasibility criterion for the Beam Bridge. The merit criteria is the bridges are being measured on their individual performance ratios and their ease of construction for the merit-based criterion. Each of these criteria are worth 50% of the overall merit points given to each bridge because they are both deemed of equal importance when choosing, modeling, and constructing the bridge. This is the ease of construction merit curve. So the easiest bridge would have been given 10 merit points, while the hardest bridge would have been given 0. And our bridges all fell between 0 and 10, but none of them were 0 or 10 because we had to be between the easiest bridge and the hardest bridge possible. This is the performance ratio merit between 0 and 3,000 for the performance ratio, which is the lowest possible point and a little bit higher than our bridges fell under. So 0 would have been given a 0 merit point, and 3,000 would have been 10 merit points, and our bridges fell in between those points.
So now we're on to the design alternatives. And so we had a 3-person group, so we had 3 different bridge alternatives. The first one, as you can see, is a subdivided Warren done by Abigail. The next one is my Pratt Bridge, which is really similar to Connor's bridges, which is the one we eventually chose. And this is Connor's bridge, which is, like I said, the one we chose. So the feasibility analysis, we just went over the criteria we needed. So ultimately, our bridges all met the feasibility criteria, and this is labeled by the O's right here. And as you can see on each column, all of them are checked off. So all of our bridges were feasible. Now on the merit analysis, we just talked about the performance ratio and the ease of construction as our merit criteria. But before we get into that, we're going to talk about a little bit about the predicted models that we built for each alternative. And so my Pratt Bridge, the predicted weight was 10.24 grams. The failure load was 18,914.8 grams. The performance ratio was 1,895.45, and the predicted safe load was 9,457.4 grams. The subdivided Warren Bridge, Abigail's bridge, predicted bridge weight was 24.95 grams. Predicted failure load was 8,073.94 grams. Predicted performance ratio was 323.6. And the predicted safe load was 4,036.97 grams. And the Connors Bridge, The Warren Bridge with vertical supports. The predicted weight was 6.8 grams. The predicted failure load was 15,076 grams. Predicted performance ratio was 2,479.45. And the predicted safe load was 7,538. Now onto the specific merit analysis. We talked about starting with the performance ratio. My Pratt Bridge received 7 points out of 10 for the performance ratio of 1,895. Abigail's subdivided Warren Bridge received 1 merit point for the performance ratio of 323. And Connor's Warren Bridge with the vertical supports received an 8 merit points for the 2,479 performance ratio. The ease of construction, the subdivided Warren, which was Abigail's, received a 1 because of the number of members and joints it took to build that bridge. And then the Pratt and the Warren Bridge came out pretty even with the number of joints and members, so they both received an 8 for ease of construction. This is an easier view of our merit analysis. Like we talked about earlier, ease of construction and performance ratio were 50% each. And then you can see the totals on the far right of each bridge, and 150, 750, and 800. So ultimately, we went with the Warren Bridge with vertical supports because of the 800 merit score.
All right. And after all that, Tanner explained, we're going to go with the recommendations that our designs had. The one that Abigail did, the Warren Bridge, received a total of 150. And that was the lowest merit performance we had, along with being the hardest construction. So we didn't go with that one for obvious reasons, being so hard to construct. The Pratt came in next with 750 merit points, which was a high performance. But then with the Warren Bridge of vertical supports, actually went a little higher with 800. With the both of them having easy construction, we relied on merit points here to take a look and to change and to divide which one we wanted to do. So at the end, the Warren with vertical supports was what we went with the highest merit score. The next part is the testing plan. Testing plan was conducted by Dr. Mack. We witnessed it over a Zoom session. So we analyzed how the plan went through. First, he weighed the bridges, and then next he pushed a block under it to see whether it met that height clearance criteria. Then he put a weight harness that was constructed of a string or a chain with a eyelet and a wooden block that sat on top of our trusses here. Then he hooked a bucket under it, which then he placed sand into it. And the bucket was hooked up to the bridge through the harness, obviously. And he kept filling it with sand until the bridge failed and broke. And after that, we measured our performance ratios, and he weighed how much the sand and bucket and the harness apparatus all weighed, put it on the scale, and we got our full weight of failure from that. The results of it, all 3 Warren bridges are then compared to the predicted measurements. The tested and the predicted measurements are compared at the bottom here. I guess what we're looking at is designing more triangles in the bridge construction by adding more cross members on the sides. We noticed a lot of failures there. Would help it hold more weight, and lowering the weight of the constructed bridge would allow for higher performance ratios. I'll get a little more into it next about the comparison of the two, of the Model Smart and the real life construction. And this will hopefully clear it up a little better. None of the bridges matched what the Model Smart predictions were. All 3 bridges had a lower performance ratio than the one that I modeled in Model Smart with 2,479.45. We were actually well below it. And then all of them we built heavier than what was in Model Smart due to either human error or lack of understanding of how to construct the best. We couldn't match the weight. So therefore that would push the performance ratio way down. And that is how they matched up with the 2. The conclusion here, Well, first off, I know that's a lot on here, which we can read, which we can look at if we want. But we learned that how to use Model Smart, how to build bridges using hot glue and the balsa wood that was supplied from Dr. Mack. And we learned that how to, overall failures of bridges and how to test bridges, I should say. But at the end of the day, we understood that the model bridge is not going to compare to the real life bridge. That was the biggest part. And the intricacies of how to make triangles into a bridge will also make the structure stronger. And putting cross members in certain areas, such as the supports, would allow for more weight to be held. That is our presentation. I hope you enjoyed it. Thank you for a great year, Dr. Mack.